Hi there, welcome back. Today I'm continuing on my machine learning project. Last video I was able to create a script using ChatGPT to generate cropped faces for my videos. Okay, so you can see here. Okay, these are generated. No, it was here somewhere. Okay, so my data that I'm pre-processing is in here. So the input data that I have is here, these videos. Okay, and then I've pre-processed these videos and I generated subfolders, one per video. Okay, let's make sure you can hear me all right. A second. Yeah. Right, so I created a subfolder for each video, and then you can see that each video has segments. So in the Wave2It paper, it says that they process a video in segments, like for example 5 frames at a time. I also converted, of course, the video to a set frame rate, and then you can see here the output I did. Well, I did the last in the last episode. Like, okay, this rectangle I will remove it. This was just for testing the math detection to see whether it would be any useful, but I don't think I need it because well, for the purpose of Wave2It, I need to mask the face. Okay. And for me, I think it's enough for now to just do half of the face, and I should be able to most of the times cover the lips that way. Later down the line, after a lot of experimentation, I can always reconsider this if I want to improve the results. But for now, I think this is okay. All right. So this is the original frame. This is the cropped frame. Actually, this is a good test to make, right? To make sure I'm not just. I think it should match, yeah? Yeah, I think it's the same, okay? So today, the goal is to generate some Mel Spectograms for each segment of audio. You can see the audio I have here, okay? So the Mel Spectrogram, I'll just go into this notebook and I'll show you what a Mel Spectrogram is. Okay, so let's run this and hopefully this is straightforward. So I have a function here. I already have some code here, right? I'm just I think I already have all this, so I'm not going to run this cell. And I'm just going. So I'm going to use the WebBrowser library, which helps you manipulate sound files, okay? And using the audio that was previously extracted, it will generate a diagram that might mean a lot to you or might mean nothing to you. But I'll try to explain it, right? Not like, okay, so the normal Hertz scale is not very helpful, right? In terms of distinguishing differences in sounds, the higher in the spectrum you go, okay? So the Mel Spectrogram is a way to normalize the differences between sound levels, okay? And in this way, it's easier for a computer to apply machine learning, an algorithm, right, to try and decipher what is being said in that audio. So it's just a way to distinguish, okay? So our lip sync discriminator that we are trying to train as part of Wave2It needs to detect differences in sound, right? And it is much better if we use a Mel Spectrogram for that purpose. Of course, this is not the only way to do it. There's many other visualization. There's many other machine learning techniques for sound, but this is the most popular Mel Spectrograms. Okay, and you can see a graph here. So what we'll do today is take a wave file and we'll convert this into some kind of tensor, which has, I think it's going to have 80 dimensions. Okay. And then I'm going to store it for now in a file, a NumPy file. Okay, so that, but like my goal is to maybe in the next session that we do is to create a data set loader, a custom data set loader for PyTorch, so that we can just, because I'm preparing all the data, right? At the moment, I'm preparing all the data that I need for training, okay? So all of these are things that will be used during training, okay? Of course, with the new Wave 2 IP, I'm going to have to apply an encoder, a VQGAN encoder to compress these images, right? Okay, so all of the data that I'm going to pre-process is going to be in a very non-standard format, right? So when I'm done encoding this image, you will not see the face anymore. It's going to be just like a binary file. You can't really see what's inside it until you decode it. Okay, so all of these files will be non-standard. So what I really want to do is to create a dataset loader in PyTorch that can just load this data from disk into the correct format, like the correct type of NumPy arrays. That's it. Okay, all right, let's get started. Okay, so let's go and first of all, see how much work can, okay, maybe I'll just take this square off for now. Just go back to the previous code I had, remove that before I forget. Okay, so I had created this crop faces script, and I can remove the rectangle from here. Okay, I think I did. No, I already removed it. All I have to do is just run this again. Next time I'll run it. Okay, for now I'll just keep it. All right, so let's see. Let's go to ChatGPT, and hello. I need to generate a Mel spectrogram in NumPy format for each .wav file that I have inside a folder or its subfolders. Okay, so I'm making sure that, yeah, that I'm telling ChatGPT that these sound files could be anywhere inside the directory. For each sound file found, generate Mel spectrogram using Python, ready to be used in training, and save it to a binary file, and save the resulting NumPy arrays to a binary file. Okay. I think this is okay, right? So I need to generate a Mel spectrogram in NumPy format for each WAV file that I have inside the folder or its subfolders, and for each sound file I found, generate a Mel spectrogram of features like, let me just add that, because it's one thing is to generate a Mel spectrogram for visualization, another thing is for training, using Python, ready to be used in training, and save the file, the result, okay, and save the resulting NumPy array to a binary file, okay, with the same file name, except that the extension should be .npy. This should be easy. Okay, let's see what it says. Okay. Okay, so we have now, I think ChatGPT understood what I wanted, so it's just now writing the code. I love that. Let's see. So this is going to save me probably at least a few minutes, you know, trying to just copy and paste a ready-to-use code from the internet. Yeah, so I'm not really doing much, anything different that I would do before. That I would not do before. Like my previous, before ChatGPT came along, I used to just search for solutions on the internet anyway, so it's the same thing. Okay. All right, so it gave me some code, and so let's see what this is actually doing. So it's taking, so this is a function to generate a Mel spectrogram. Okay. But I don't think, number of Mels, it defaults to 120. I think in the wave tulip paper, I have it open here, how many, they detailed how many they used. So Mel. I think they use 80 features, but Mel spectrogram. Okay. Okay, anyway, I can adjust that later. It doesn't really matter for now. But I think it's 80. Okay, so it's opening the file, reading, getting the Mel spectrogram, and then returning it. Then it saves it to a NumPy file. Okay. And I'll specify. I'm going to tell ChatGPT to use argparse. For the arguments, so I don't have to just hardcode everything. Okay. So what the wave tulip paper is using is a ResNet model, and they've adapted the ResNet model to accept RGB images and audio, right? So it will take two pairs of data. One is the RGB images, and then it will be a set of frames, and then an audio for that set of frames. So we are currently trying to generate the data that we are going to give as input to this ResNet model that we need to train for the lip sync discriminator. Okay, this is good. Already have, yeah, awesome. I don't like the parameter name, but you know, you can change it easily, and then you even decided to create an argument for the number of Mels with the default, so I don't have to always specify it. So I'm going to copy and paste this code. Okay, and I'm going to go into okay, so I have here the scripts. So all the scripts I'm going to afterwards use in a data pipeline, which I will assemble with some configuration, and then yeah, they can be run regularly or whenever I need to run them on demand. I'll probably do a separate video on that, how we could use, for example, Argo workflow to just create a data pipeline using these scripts. So in this case, I'm going to call this script, what's it called? Generate Mels. Okay, .py. Right, that's Anyway, that's probably very similar to the name that ChatGPT came up with. So we have generate mails, and I don't like the name of the argument, but like, what can I call it? Let me see if I can be consistent with previous scripts. Oh, these scripts, they don't even have arguments. The one from yesterday had arguments. So the argument, yes, the input directory. Okay. Just call it input directory, just at least to be consistent. Normally, you can just do this, input directory. Don't have to put the underscore. Right? Okay, so let's try. I also want to have a default, so I don't have to always to pass in this argument. So I'll just set the default equal to, and I'm going to copy it from the other script. Actually, I'm going to copy it from here. For now, all these names are just maybe not the best names, but I can change it anytime I want. Okay, input directory, and it should go into the same directory, so I didn't specify an output. Okay, so I should have the required libraries here. If not, I will just install it. Okay, so if I go into source preprocessing, I can try now running generate mouse. The root folder, okay, it's looking for the root folder because I didn't change the name. Okay, here. So input directory. Okay. So now, okay, another error. I didn't pass in. What happened there? Line 8. Okay, so it seems like it okay, I have some errors. I don't know if this is a bug. Sometimes ChatGPT is wrong, so we just have to always check. So, well, quite often, right? I would say you have to really check. So I'm trying to understand what is the file path that it's trying to load. So to see if it's actually trying to load a correct actual file. Okay, you can see it's loading this WAV file. Okay, so let's see what it's actually like. It's a very short one. Okay. Oh. Yeah, okay, it's very short, but that doesn't. Okay, so the actual file is correct, it's valid. Then page fails. Well, I do have code that works. So here, this is the. So what's this? SR. Okay, so let's do another print here. Okay, print. See if we. I'm just checking if we're getting actually valid data. Okay, so we get valid data here, so it's correct. So it's actually complaining. This Mel Spectrogram method is complaining that it's getting one argument, this one, and it only takes 0. So this may be deprecated code. So let's have a look at the previous code I had here. Oh, okay, so as you can see, all of the arguments are named arguments. So this is out of date. Should be able to fix this easily. Okay, so this is audio, right? So audio equal to, okay, let's try it now. Okay, input signal must be provided to compute a spectrogram. Okay, let's see, where is it saying that? Oh, is it y equal to? Okay, got it. Maybe y equal to. Sorry, I made a mistake. Okay, that's the audio that I needed to set, but it needs to be y equal to y. So this is audio. Okay, now it's doing it. It's working already. So let's see. Okay. All right. So let's have a look at. I'm hoping it didn't just overwrite the WAV file. Okay, you can see here, right? This is a NPY. This is a NumPy array. I'm going to open this in the text editor, but it's a binary file, right? So this is a NumPy array, which I could load then during training. Yeah. And okay, so now, okay, it was fairly easy to get this working, right? So I'm going to spend a bit of time just going to the actual wave2 code, just to make sure that we have these parameters more or less correct. So I wanted to have the same type of parameters they had, and I believe they had 80 mels. So 1 second, I just need to do something off screen. Okay, so we have here the source code for wave2. Okay, I'm trying to not copy the source code because I also want to understand how all the decisions that were made when creating these models, so that when in this way, right, rather than just copying, I can actually improve, right, by maybe later on, by understanding every single aspect of the model, then it's easy to tune it later. Okay, so we have here a file called audio.py. Let's see. They have actually a configuration file somewhere here, which details like the different parameters they have. Okay, HP params. Some number of mels. Okay, 80. Okay, that's what I remember that. And then they have this rescaling audio. I'm not sure. I'm not 100% sure why this is needed. And rescaling max. I think this is to do with those parameters that you prove. Okay, I'm just going to search for this parameter and see what's being used. No? Is it being used? Okay, this is evaluation. Okay, maybe, I don't know if it's being used for training actually. I don't know if the search is what is very accurate. I probably will download this at some point. Okay, so pre-process. I don't think it does the audio here, does it? Okay. So it's calling a command for the audio. Okay. Okay, so this is the command. It's actually calling. It's an ffmpeg command. And they are using that to okay. Let me just copy this and I'll ask ChatGPT what what this is actually doing. See if it can figure it out. I know that. Yes, I know what ffmpeg is. Okay, the low level, it's not really important. Okay, this is without confirmation. Actually, this is not much. Maybe I think I understand what it's actually doing here. This is not much. This is just to extract the audio. Nothing big deal. The pre-processing of the audio, anything else that's done, it's not done here. I don't think they do any ML. Face alignment, that's another thing. Okay, fine, this is what the script is doing. So we know that it's 80 mel. So audio PY, this is the important file. Okay. You see, I don't want to actually just take all the complexity that's already in the model. Probably would be quicker if I just ran the model and modified it, but I also want to understand as much as possible about why all these codes are there. Symmetric, okay. All right, so this is what we have in the original source code. For now, I have a very simple function that takes audio files and generates a Mel spectrograms and then dumps it into a NumPy binary file. Okay, that's about it for this task. I will end here because this is like the task I had this is a good point to end, and I will see you again in the next video. I will be looking to put all of these pre-processed data into a format that is going to be efficient for PyTorch to load during training. Okay, I'll see you again soon. Happy coding!